I'm Ahmed Daud, and in the last session we have seen precision, recall, and F1 score. We have seen some aspect where we can use precision, recall, and F1. So in today's session, we will discuss some key points regarding binary classification and regarding these maze that we already have studied. First of all, one recommendation for you: whenever you have binary problem and you have imbalanced data set, always label majority class as 0 class and minority class as 1 class. Whatever class you have, let's say you have a target column here, and in the target column you have two classes, let's say class A and class B. Okay. Uh, Whatever class is in majority, let's say if A class is in majority, you simply label, or when you convert this categorical column into numerical column, just convert this into 0 class, and the class which is in minority, you convert it into one class. Oh, the reason is that it will be easy for you to select the performance measure. You will not get confused when you will follow that way. Okay, and we will also discuss the intuition of doing this or behind that recommendation. Okay, so in the last session we have seen four measures: accuracy, last sessions, accuracy, precision, recall, and F1. And whenever you have to select performance measure for binary problem, you have a data set, and first you have to check what type of data set you have. If you have balanced data set, means equal number of zeros and let's say number of ones and number of zeros are almost equal to each other, equal to number of ones and zeros you have in your actual data set, then you can use accuracy. No matter for which error you are more conscious. If you are conscious about false positives, false negatives, for both, you can use accuracy. And we will also discuss what's the reason behind that. Second, if you have imbalanced data set, means you have number of zeros more compared to number of ones in your actual data set, then you can say it's imbalanced data set. And in that case, you have to ask the question about which error you are more conscious. Okay, so if you are conscious more about the false positives, you should uh, prefer precision score for your evaluation metric, and you want such a model which has high precision and good recall. Whenever you are curious more about the false negative, you should prefer high recall and good precision. Whenever have uh, you are conscious about both errors, you should prefer to choose F1 score. Okay, so these are the simple formulas regarding that: accuracy and precision and recall. Simply, accuracy is true predictions divided by number of false samples that you have evaluated, and this will be like this: true predictions divided by all the samples that you have evaluated. It's accuracy. Uh, this and divide by all the cells. Okay. In the case of precision, you start already from the side of prediction, true prediction, and what is actually precision? The accuracy of positive predictions by your model. Okay, so how many samples your model has predicted as one, and out of one, how many are true positive? This is actually the precision. Okay, this is precision. And on the other hand, recall is how many positive samples you have in your data set, and out of these positive samples, how many are correctly classified by our classifier. So this is recall, and in that case we are more conscious about the false negatives. Okay, true positive out of all the positives we have in our data set. And when we have let's say F1 score, and means we are conscious about both errors equally, and in other words you can say both errors equally dangerous for us. So in that case we calculate the geometric mean, or you can say mean of precision and recall. Okay, it get all three cells. Okay, so this we already have studied. Okay, so first of all, we will discuss uh, what is the actual intuition behind that. If you have balanced data set, no matter about which error you are more conscious, you can simply use accuracy. Okay, so we will see here. Okay, so it's very obvious whenever you have balanced data set and you train a model on balanced data set, is usually we will get a balanced model. What exactly mean by balanced model? That in the predictions column, in the prediction, you will have equal number of ones and equal number of zeros. Okay, because you have trained your model on the balanced data set. Okay, and in other words, you can say your model has seen equal number of samples regarding to each class during its training process, so it is equally sure to predict the sample for both of class. And in that case, if it is equally sure for both classes, then you can see that your true positives and true negatives are almost equal to each other, and false positive and false negative will also equal to each other in case of balanced model. Okay, your model will be equally sure for both classes. Okay, if it has positive false positive errors, then most it will have false negative errors approximately equal to the false positive number of errors. So in that case, when you have equal number of true values or true samples and equal number of false predictions by your model, then you will see that your accuracy, this is your formula of accuracy, and when you will pass true negatives equal to true positive and false negative equal to false positive, your formula of accuracy will become equal to precision. Okay, and in the other way, if true positive equal to true negative is equal to true positive, and false positive is equal to false negative, you will put these values, then your accuracy will be equal to the recall. It means when you have that type of case, and that type of case usually occur in the case of balanced model, or you can say the in the case of balanced data set, then your accuracy, your precision, your recall, F1 score is also will be equal because precision and recall are the same. And if you will take an average of precision and recall, it will be also the same. So in that case, when you have this type of scenario, your precision, accuracy, recall, F1 score, all are giving the same result, same score. No matter about which error you are more conscious, you can use simple accuracy. You don't need to go for the precision or recall and F1 score. Okay, because here accuracy can explain both errors. Let's say if your model is giving 90% accuracy, then it means that there are 10% errors in your model, and regarding both you can say regarding both classes, you will have false positive errors and false negative errors also. Okay, and it can also accuracy in case of balanced model, balanced data set, accuracy can also explain the or also detect the dumb model. Okay, like if you can see here, we have discussed the negative dumb model, and if your actual values, let's say your actual values here, y is like that. Okay, you have 10 values here, and 1, 2, 3, 4, 5. Okay, against your 5 samples, your model has done the wrong prediction here. You can see in this case, in the fifth case, and in the last these cases. Okay, your model has done the 5 wrong predictions and five true predictions. So here will be 5/10. Your model is giving 50% score. Okay, and it is pretty sure that your model is not good here when you have 50% accuracy. Okay, it can detect also that. So it is in the case of dumb model, but in the case of when you have normal model and you train a normal model on the balanced data set, you most chances that you have equal number of ones and zeros in your predictions, and also your true positives, true predictions for both classes will be similar to each other, and number of fast predictions also the same for both classes. Okay, so I hope you got the idea why in the case of a balanced data set, no matter about which error you are more conscious, you can use simple accuracy. Okay, because accuracy can explain all the errors in case of balanced model, in case of balanced data set. And it is very obvious that in the case of balanced data set, you can achieve a balanced model. Okay, and it is keep in mind a normal model can be a balanced model. Okay, whenever you will pass a balanced data set to a normal model, it can be you are able to get the balanced model. Let's say if you are using some abnormal model which is already faulty model, then in that case maybe uh, you will get some unbalanced model, although you are passing balanced training data points. Okay, but in case of normal model, you are already you will easily get the balanced model. So in the case of imbalanced dataset, it is not as simpler as compared to the balanced scenario. In case of imbalanced dataset, you have to ask the question about which error you are more conscious. What is the reason here? In the case of imbalanced dataset, like in the case of balance, in case of imbalanced dataset, whenever you have imbalance, you will get a unbalanced model. When you will train your model on the imbalanced dataset, it is pretty straightforward that you will get unbalanced model. The reason is that if your model has seen more samples of one class during its training, then your model will be more sure to predict that class during its prediction or during its uh, during the testing phase. Okay, and if your model has seen very less number of samples during its training phase, then your model will not be able, and it will be less sure to predict that class. Okay, and ultimately you will have imbalance, or you can say in the case of imbalanced data set, you will have unbalanced model. Okay, so imbalanced model means that in the case of predictions, you will have number of ones uh, and number of zeros not equal to each other. Means you are uh, one like one class will be in a majority and one class will be in minority in your predictions. Like here, if you will have this type of data set, which is imbalanced data set, and I also have recommended you always use more majority samples as zeros and minority samples one. So in case of imbalanced data set, if you have this type of scenario, you will pass this data to a normal model, uh, uh, not abnormal model, basically. And when you will pass this type of data set to your normal model, then in the predictions column, you will also get more zeros and less ones. It is very obvious. Okay, like it is if you think in the other way, it will be very weird. Like if you have let's say 100 zeros and just 10 ones, and you have trained your model on this data set. Okay, on this data set, and then you will test your model on test your same model, then you will get uh, let's say again you are testing your 100 zeros and let's say 10 ones. Again you are testing in that way. This is the training phase, and when you are doing the testing phase, okay, and you will get 100 ones and 10 zeros. It is very weird to think in that way that your model has seen more samples belonging to zero during its training phase, but it is more sure to predict one class in the testing phase. It is very weird, and it is very, you can say, absurd in terms of thinking. Okay, very absurd it is. And it can be a faulty model or abnormal model if in that case. Okay, your model has seen more samples related to zero class, but it is more sure to predict one class. It is very weird in terms of thinking also. Okay, so in simpler way, we can say here, in case of balanced Dataset, you simply get the balanced model, and if you are getting balanced model, it's very straightforward that you can use accuracy, uh, if no matter about which error you are more conscious. And in the case of imbalanced model, you will fall into the unbalanced model, and in that case you have to decide about which error you are more conscious, and you will use uh, the scores according to the requirement of your consciousness about some particular error. Okay, now here we will discuss another aspect. Okay, another key point here. Okay, so in the case of imbalanced dataset, you are using these measures like true positives, recall, F1 score. Okay, you are using these measures here, and here you can see easily that in the case of precision, you are just scattering. If I will remove this, okay. So in the case of precision, you are just scattering two cells. Let's say these cells in case of precision, and in the case of recall, you are just scattering these two cells of the confusion matrix. And in the case, you can say that because you are just curious about one error, that's why you are scattering two cells. But in the case of F1 scale, when you are caring about both errors, false positive and false negative, again you are just scattering these three cells. Okay, true positive and false positive, false negative. And here you have got an idea that you are not caring about the true negative. What is the reason that you are not caring true negatives, and you are not using true negative in your formulas of precision, recall, and F1 score? In case of imbalanced dataset, why you are not caring about true negatives? Okay, what is the intuition? It is one way is to thinking that if you can get some good result and you are fulfilling your requirements by having any type of formula, then you are already satisfied with that. But if you want to know what can be intuition, why we are not caring about the true negative in the case of a imbalanced data set, we have precision recall and F1 score, and we are not having true negatives in these formulas of these measures. Now we will discuss that. Okay, why precision recall F1 have not true negatives? So these measures we usually use in the case of when we have imbalanced data set. And when you have imbalanced data set, you are pretty sure that you have more zeros and less ones, because in the recommendation I have recommended that always majority class will be 0 and minority class will be 1. If you will train a model on imbalanced data set, you will get unbalanced model. It is pretty straightforward here. And then more sure about when you have unbalanced data set, unbalanced model that you have trained on imbalanced data set, then you are pretty sure to predict the zero class compared to one class, because you have seen more samples of zero class during your training process. Then you will be more sure to predict the zero class. Okay, and you will be less sure to predict the one class. So in that, for that reason, we usually uh, for that reason we have this type of predictions when we have again more number of zeros in the prediction and less number of ones. And for that reason we are more conscious about the one class, because we already know that if our model is trained on the imbalanced data set, then our model will be sure to predict the zero class, but it will be less sure to predict the positive class. So for that reason, we care more about the positive class in the case of imbalanced data sets. When we figure out that we have imbalanced model, then we go towards these formulas, and we already got an idea that we should be more care about the one class. So there can be two type of errors, like when one class will be predicted as 0. Okay, and there will be second error when zero class will be predicted as 1. Okay, when your actuals are these and your predictions are these two type of errors you can have. Okay, first error, like a positive sample incorrectly classified, and model's positive prediction is false. This is false negative. Then when your positive sample incorrectly classified here, and when your model's positive prediction is false, then false positive, and when you are carrying equally about both errors, then it will be this scenario. You will have three scenarios, and according to three scenarios you can choose your required measure accordingly. Okay, for that reason, we in the case of imbalanced data set, we usually care more about the true positives, positive class compared to the negative class, and when we and but we are caring about both errors. In the case of positive class, we can have for both type of errors, when one as 0 and 0 as 1, and we are caring about all errors, but we are uh, in the terms of positive and true negative, we are more caring about the true positives, and it can give you the good result also. Okay, and you are pretty sure that your model will be able to predict negative class accurately, but there is less chance that your model will predict positive class accurately. So we usually prefer that precision recall F1 score in these type of cases to evaluate our model. So now there is another scenario that is there any formulas, any measures in which true negatives are? Okay, so we will see here. There are some measures also in which there are true negatives are using in their formulas. Like here you can see in the case of recall, we usually have recall also called true positive rate, and recall also called sensitivity. We say that about the one class, that what is the accuracy of one class, you can say this is the actually the recall, how many positive predictions or how many positive samples are correctly classified, it is actually the recall. Okay, and you have generated this formula from confusion matrix. In the same way, you can generate another formula from the confusion matrix in which you are caring more about the true negative class. Okay, in terms of true prediction, you are more caring about the negative class. So it will be a true negative rate. True negative rate. And in the other words, you can say recall for the negative class, or accuracy of the negative class, you can say in that way. So what it actually means, that how many uh, how many chances or how many number of negative samples are correctly classified. This is true negative rate, and here you can see true negatives are you are using in the formula. There is also you can generate this type of formula, which is not like a score, it is like a error rate. Okay, false positive rate. Okay, here you are caring about how many samples out of all negative samples, how many samples are incorrectly classified. So false positive divided by false positive plus true negative, this is all the negative samples, and these are the negative samples that are incorrectly classified by your model. So this is the error rate, false positive rate, and you usually want a less false positive rate because it is not a score, it is a error rate. Okay, and you have seen in both formulas you are using true negatives. Okay, so but we usually recommend these recall, precision, and F1 score in the later sessions. In the case of ROC curve, when we are discussing ROC curve, we will uh, discuss a curve that will be generated by true positive rate versus false positive rate. Okay, in that ROC curve lecture, we will discuss this in the more detail. But for now, you can see here, uh, we usually prefer in case of imbalanced data set recall, precision, and F1 score. These measures. And you have seen that there are also measures in which true negatives are present and true negatives are using in the formulas. And keep in mind, always I am talking about the general scenarios. Okay, always keep in mind with respect to maybe your problem statement, your project requirement, maybe you will need some other type of measure. Okay, but for the general scenario, I am telling you here. Okay, so here another aspect that maybe you have in your mind, that there is no such a measure that we have discussed till now in which all the four cells of the matrix are catering. Okay, like here you are getting just two cells, here you are getting again two cells, here again you are getting two cells, and there is just one measure that we have discussed, F1 score, in which we are catering maximum cells. And the reason is that for the because we are caring about both errors equally. But again, in this formula also, you are not caring about the true negatives, and you are not catering all the cells of your model, of your sorry, of your confusion matrix. Okay, you are just catering three cells, you are not catering your fourth cell, which is true negative. Okay, so maybe the question in your mind, that is there any evaluation metric in which all the four cells we are catering. Okay, here you can see in the case of accuracy, you have this type of formula in which all the cells you are using in the formula. But it is for the balanced model, or in the case of imbalanced dataset or unbalanced model, is any metric which is having all the counts in its formula. Yes, there is a measure which usually called Matthews correlation coefficient. So now we will discuss Matthews correlation coefficient here, and it is also symmetric. Okay, so we will discuss that in detail. So what is Matthews correlation coefficient? Matthews correlation coefficient, from the correlation coefficient, you can get an idea. We have discussed in the case of data preprocessing, EDN data preprocessing, uh, correlation matrix, correlation coefficient, covariance, this type of stuff we have discussed. And when we are using this correlation coefficient, when we want to see the relation between two continuous variables, when we have some two continuous variables, and we are caring about how much they have, we usually use covariance for the purpose when we are just caring about is these two variables have positive correlation, positive relation between them, or negative relation. And correlation for the purpose that how much they have relation, what is the strength of relation between these two continuous variables. Okay, the same interpretation you can use here, and this is the Matthews correlation coefficient. Here you are measuring your association, measuring your relation, strength of the relation between two binary variables instead of continuous variables. Between categorical variables, here you can say. Okay, instead of continuous variable. The same interpretation is here. Let's say you have a column which is actual values, and here you have 1 0 0, and in that way values, and there is another binary column which is prediction. If I will show you here prediction, and again there will be 1 0 and 0 and so on. Okay, these are two categorical columns you have, and if you want to see the relation between these two columns, correlation, how much they are related to each other, is they are how much they have strength of relation between them, so you can measure by using Matthews correlation coefficient. Okay, so this is the interpretation behind MCC. In statistics, we usually call it as a phi coefficient. In machine learning, we are saying that it is MCC. And here you can see it is a measure of association between categorical columns. And in terms of interpretation, it is same as the correlation coefficient that we have discussed for the continuous column. If I can show you here, yes, here you can see in the case of correlation, we have this type of formulas, and we are here finding the correlation between X and Y. Okay, between X and Y, how much they have correlation between each other. Okay, and this type of formula we were having, and in that case, so we by using covariance, we can find out is are they having work experience and salaries, are they having positive correlation with each other or negative correlation with each other. And when we want to see the strength of the correlation, then we actually to eliminate the units, to eliminate the units, and to scale our um, strength of the relation in between -1 to 1. We divide our covariance formula here by you can say we have divided this covariance formula by the standard deviation of work experience into standard deviation of salaries. Okay, this intuition we have discussed in the case of continuous variables in AD and data preprocessing part. And here in the case of Matthews correlation coefficient, you are also having the formula, and here you have this type of range. Again, as I discussed, that range is here like in the continuous variable coefficient, correlation coefficient, Pearson correlation coefficient, you are having range -1 to +1. In the same way, MCC has range between -1 to +1. Okay, here you have this type of formula. If I will show you here, this formula, true positives into true negatives minus false positives into false negative. Okay, so this is in the numerator, and in the denominator you have true positive plus false negative into true positive false plus false positive, true positive plus false negative into true positive plus false positive, and then square root of that. This is the denominator. And in the same way, like in the Pearson coefficient, correlation coefficient, you have denominator just to scale your uh, value in between the range of -1 to 1. In the same way, the denominator has the same working here. Okay, and main part is your numerator. Here from the numerator, you can see that you have four cells, all the four cells of your confusion matrix. If I will 0 1 0 1 predictions here, and here are actuals, and you will start from here, negative negative, positive positive. These are the true negatives, these are the false negatives, these are the false positives, and these are the true positives. And you are capturing all the four cells here, you can see in the metric of MCC. Okay, that's why it is also called a symmetric metric. Okay, that's why it is called symmetric metric, and it is also covering all the four counts of confusion matrix in this formula. Okay, and now we will discuss where we can use it. And before that, it has three values, like range between +1 to -1. When your model means your model is perfect, or you can say your relation between your actual and predictions is a very good relation, means your false positives are also 0 and false negatives are also 0, means you have no error. In that case, you will get +1, and you can see your model is perfect here. Okay, or you can say ideal model you are having here. And on the other hand, when you have MCC 0, it is actually very bad model you are having. Okay, in that case, means your actuals and predictions have no relation between them. Okay, when you have MCC equal to 0, and when you have -1 and some negative value of MCC, then it is you can say that you have some fault in your model, because you are in the case of -1, you have true positives and true negatives both equal to 0, means you have 0 true prediction and all the false predictions. Then there will be some fault in your model, that it is behaving in opposite direction. Okay, you have to care about the structure of your model. But when you have 0 value, or more than the 0 towards the positive one, then it measures how much positive relation between your actual values and the prediction values. And in this way you can also check the model performance. Okay, you have discussed that. Now where we can use MCC, like we have discussed in the case of imbalanced data set, we can use multiple measures, and I have also discussed here that MCC used in the case of imbalanced data set. So about which error we are more conscious, that we at which case we can use MCC. So here use cases in case of imbalanced data set, and when you are caring equally about all the classes, or you can say when you are caring same for the false positive and false negative, both errors are equally dangerous for you. You use, or you can use MCC, like you can use F1 score. In the same way, you can use MCC score. Okay. So here you can see that then what is the difference between F1 and MCC? Here by formula, by structure, you have seen that MCC having all the cells of your confusion matrix, while F1 have three cells of confusion matrix. Okay, you have seen from the formula also. Then you have seen that use cases both can be used in the uh, same scenario. Then what actually the difference between them? Okay, so we will discuss also here, as MCC is having all the cells in their formula, so that's why it is more informative as compared to the F1 score. It is very clear. So binary classification problem, and the reason is that it is covering all the four confusion matrix cells. Okay, so now we will discuss one example and then we will compare MCC with F1 score. So let's say you have this example in which you have confusion matrix like this, uh, like this. Okay, you have this confusion matrix here, and here in that case you have actual values on this side and prediction values on this side, and you have false positives, 5 false positive and true positives 95, and there is zero prediction regarding the negative class here. Here you can see both true negatives and false negatives are zero here. So when you will calculate your accuracy is giving 95%. Accuracy is simply that divide 95 by sum of cells, which will be 95 by 100. It is accuracy. In case of F1 score, you are getting 97% score. The reason is that in the case of precision, you are having a formula like 95 divided by 100. Your precision will be 95%. In the case of recall, you will have 95 divided by 95. Uh, it will be 100%. It will be 9, precision will be 95%. In that case, recall will be 100%. And when you will take average of for geometric mean of precision and recall, you will get 97.44% F1 score. So according to accuracy and F1 score, this model this model is quite good, very good. But here you can see it is just a positive classifier. It is very bad model. Here you can see, here you can see it is very bad model. It is just predicting positive class. It is just a positive classifier. It is just a dumb model. It is not predicting even a one sample for the negative class. But here your F1 score is saying that it is good model. On the other hand, when you will calculate the MCC score for that uh, confusion matrix, you will have undefined value, and from here you can see that you can easily identify that your classifier is going in some wrong direction, because you are not getting MCC score good here or proper MCC score, and you are achieving undefined value, means you are there is something wrong with your model, with your classifier. And here from here you can see that you will say that MCC is uh, very good as compared to F1 score. But here as I have given you the idea, let's say you have this confusion matrix again. Here you have actuals, here you have predictions. Okay, 0 1 and 0 1. Okay, so here you can see that in that case, in this confusion matrix, you are having actual samples of zero samples. If I will write here, okay, here in actual samples for the zero class, you are having number of zeros. Uh, how many number of zeros you are having? 5. And how many number of ones you have in your actual class? 95. Okay, and that's why I have recommended you always use majority class as 1, oh sorry, majority class as 0, label majority class as 0 and minority class as a 1 when you have imbalanced data set. Here it is doing in the wrong way. That's why your F1 score is not good here. When you will change that, here you will mention your and you will design another, let's say I will make all that. Okay, so let's say now you will follow my recommendation, and by using my recommendation you will make your actual values in this way. Majority class will be 0 and minority class will be 1. So in that way, uh, you will see this false positive will be false negatives here, false negatives, and true positive will be your true negatives, 95, and this will be 0 here. Okay, when you will just convert 0 into ones and 1 into zeros, or in other words, when you will follow my recommendation that majority class is 0 and minority class is equal to 1. So in that case, if you will calculate F1 score, you will see that F1 score here. First, you will calculate precision, and in the case of precision, true positive divided by true positive plus false positive, and here you can see true positive plus false positive, and you will get 0 value. In case of recall, again true positive divided by true positive plus false negative, again you will get 0, and mean of precision and recall will be 0, and here you will have F10. Okay, and it is very well explained that your model is not good. Your model is not good because F1 score is 0 here. Okay, now F1 score is working good, enough good here, and it is able to identify that there is some fault in your model. But F1 is working when you have mentioned and you have labeled majority class as 0 and minority class as 1. Okay, and now you have seen the difference where you can see use F1 score and where you can use MCC score. So here uh, MCC does not depend on which class is positive one, which class you have mentioned as a positive class and which class you have mentioned as an active class. Okay, if you are you don't want to depend, or you don't want to mention by yourself which class is a positive and which class is negative, and you don't want to follow my recommendation, then you can use MCC if you are caring equally for both errors. And if you are following my recommendation, then F1 scores you can simply use, and it will give you it can work as a good measure there. Okay, so MCC, what is MCC? MCC, we have seen that it is mathematically very beautifully constructed. It is covering all the 4 cells, and it is very symmetric, capture all the CM cells. And on the other hand, F1 score, it is just capturing 3 cells, but it is again giving you the uh, clear idea of the performance of the classifier. Just you have to follow my recommendation. Mark majority class as 0, minority class as 1. It is quite, then you can use F1 score. And why we can use F1 score? It is quite interpretable because of merging of precision and recall. But what is precision? Simply how many positive predictions are correct. And what is recall? How many positive samples are correctly classified. You can see how good they are in terms of interpretation. And as F1 score is the uh, average of precision and recall, so that's why F1 score is very good in terms of interpretation. Okay, and as you know, it is asymmetric, not caters true negatives. So you should make sure that you have to label this majority class. I have told you multiple times. If you follow my recommendation, like here, okay, if you follow that recommendation, then you simply you have this type of diagram. Whenever you have balanced model, you can use accuracy. When you have no matter about which error you are conscious, no matter to, like if you are balanced model, no matter to which class you are making positive and which class you are making negative. In case of imbalanced data set, then you have to follow recommendation, this recommendation. And whenever and about which error you are more conscious, you can use the evaluation metric accordingly. Okay, so for now you can think in that way that you are good to go with precision, recall, and F1 score. and you now get an idea why true negatives are not in the formula of these measures. You also have got an idea that there are also other measures in which true negatives are involved, but we usually don't use that type of measures. And I told you that in the future session, in the case of ROC, you will get an ROC curve by using recall versus false positive rate, in which you are having or catering to negatives also. But again, commonly we usually prefer these precision recall and F1 score. And you will also see the use case of ROC curve also in the few coming sessions. And in the today's session, you also have seen MCC metric and use case when you have imbalanced data set and you are carrying equally for both errors, you can use MCC score. And main advantage, when you are not following my recommendation, you can use MCC. When you don't want to depend to which class you want to make positive, you can use MCC. Okay, why I have discussed here MCC? Because in a lot of sources, when you are reading evaluation metric regarding binary uh, classification measures, you can see there are a lot of measures that we have discussed already: accuracy, precision, recall, F1 score, and you also have seen the use cases. In the same way, you will see MCC in a lot of sites or on a lot of sources. And for you to make clear what are the use cases of MCC, where you can use it, I have discussed in that session. There is also another measure which is Cohen's kappa correlation Cohen's kappa coefficient. It is also statistical measure, uh, and it is actually used to measure the reliability of two raters. And but I will not go to in the detail of that Cohen's kappa, but I am discussing here because you will see that measure in a lot of sources also. Okay, you will see MCC, Cohen's kappa, also some other measures, cross entropy and stuff like that. But for now, just concentrate on these three measures and their use cases and follow the recommendation. Okay, so now we will discuss very, it is very straightforward from the MCC. Here you can see from the MCC formula. If you want to use MCC, you want to code, you can easily have a confusion matrix and you can code manually by yourself. And if you want to see the MCC provided by sklearn, you can also use it. It's very easy. I will show you here. Okay, so you can see here, uh, I am importing from sklearn.matrix. I am importing my Matthews correlation coefficient function, you can say, or class. And here I am just passing true values and predictions like I did in the case of precision F1 recall. It's pretty straightforward, very easy to use this function, and you will get the score which is here 0.06 or 6% score. It means, yeah, that you are using that classifier that here giving you the prediction. It is very bad here. Okay, but here not the aim of to evaluate the real classifier. Just to give an idea, Matthews correlation coefficient is available from sklearn. You can simply use that. And in terms of its formula, this is the formula. And if you want to code it by yourself, it's very easy. Like we did for the case of F1 score, you can easily do for that. Okay, so for now, in the next session, we will discuss precision recall in some more detail, and as there is a different breed of threshold setting that we will discuss, and it is also really interesting, the next session. And for now, just focus on the measures, and I want to discuss here the key points. Maybe some of you are getting confused that why we are using these measures and what are the reasons, and you want to have some flow of the uh, use case flow of your selecting the measure. So I have that's why I have designed that uh, lecture specially. So for now, thank